Which size is equal to 30 comma 30. Now you can see the variables on which it has split. Open image in new tab. So overall quality is the first variable on which it is splitting. So if you see the thing, overall quality less than equal to 8.5, it is splitting based on that part. Let's see 3 to 2. See here, overall quality less than equal to 6.5. And then it is splitting the variables on based on that. You can see here, it's a 3-level tree I have plotted. You can also plot like. So what we did is we are using the Kegel house price. We have started with the decision tree regression. We built a regression model. We got the overfitting problem here. See the classic overfitting issue. R square. Then we have exported the text of the tree. Then we have plotted the tree. We have plotted the tree also here. You can see here, plot tree. Tree structure, which we have got decision tree model. Hello. Cheppandi. No. Error, you are getting an error. What happened? What error? I'll come. The list of the class in Y has only one number, which is less than and equals. Basically, regression. That's why How will you get classified around regression data? It is decision tree regression, not classifier. We are doing a regression model. Na? Sale price is numerical and continuous. Kegel house price. Last class we have done the pre-processing and regression model, right? Same data. On that we are building decision tree. Which one is not found? You have given small x maybe. Check your x on top. Is it capital X or small x? Run all the cells. You're getting error or what? Got it. Huh? Tree. Done? Yeah. So here we can see there are many variables. In this data, we have 80 variables. If you remember, we have 80 variables in this data. So let us see the feature importance. Here you can see how the variable selection can be done. If you are looking at pd dot data frame, x dot columns, comma, remodel dot feature importances. Okay, we have to round the feature importance. np dot round feature importances, comma 2. Okay, and then let us sort by index. Dot sort underscore index ascending is equal to false. So you can see here, lot of variables are closer to 1 and some will be outrightly 0. See, functional, basement exposure, these are all 0 variables. That means they are not in the tree, they are not significant variables. You can see here. Now you can select variables using this decision tree in this manner, which are above 0.0. Those will be your significant variables. So decision tree is also used as a variable selection method or feature selection method. For variable selection, that is for only numeric variables, right? For categorical and all. See, what happens in decision tree is the Gini is calculated and then the splitting methods and the variables are identified for splitting and all. After the tree is built, feature importances are calculated again. Which are important, they will be given higher score. Okay, and then it will find some variables which have least importance, and that it will give 0 feature importance. Those variables you can delete from your model. And you can build a regression model with this specific variables. It will have a regression, will have a bigger, better model compared to the other model. So if you don't want to do feature selection or variable selection on your own, you want to use an algorithm, decision tree is a better algorithm. That also is a dimensional reduction where what happens is their deletion of variables will not happen. So here we are having deletion of variables. The difference between variable selection using tree-based models is you are deleting variables here. With zero variables, zero feature importance, you're deleting them. In principal component analysis, we combine variables. We don't delete them. We combine them into components based on a correlation matrix or a covariance matrix. We use covariance or correlation. Then we calculate eigenvalues and eigenvectors, and then we combine them into components. Their variable is not deleted. It will be combined into groups of variables based on similarity, called components. Here in tree, here we are deleting variables. We are removing the variables based on feature importance being zero. So that is the difference. If you look at PCA or factor analysis, it's all combining of variables. No deletion of variable will be done. In this case, we are deleting variables. We are removing them because we found that the feature importance is zero. Even tree will also delete them. Decision tree itself will delete those zero importance variables from its model. Okay. Done. Corrected it. Okay. Plot underscore tree. No, is it plot or PLT? Matplotlib, what you have given the name? Got it? Okay. Okay. Now, yesterday we have discussed single tree model, which is decision tree. Tree-based models, multiple tree models. Multiple tree models, also called as ensemble methods. In decision tree, we get only one single tree. In multi-tree models, you can build thousands, hundreds of trees, hundreds of decision trees. The single tree we build, that same decision trees, we can specify how many we want, 1,000, 2,000, 500, 10,000 also we can build. So multi-tree models, also called ensemble methods. Within the ensemble methods, one of the method is bagging, also called as bootstrap aggregating. Bootstrap aggregating, and the popular algorithm is random forest. The popular algorithm is random forest. So tree-based models, multi-tree models, more than one tree will be built, exactly like how we build a decision tree. Same decision trees will be built, but more than one. You can specify how many you want to build. Accordingly, that many trees will be built. And we call them as ensemble methods. Within ensemble methods, the first method is bagging. Full form of bagging is bootstrap aggregating. The popular algorithm within bagging is, it's recording. The popular algorithm is random forest. Random forest is the popular algorithm. Now, the name random forest, random refers to sampling method. Random refers to sampling method. And forest refers to multiple trees. So the name random forest here means random refers to the sampling method. So random sampling is an unbiased sampling. You randomly take. You don't have any control on random sampling. A random generator will be used, and accordingly, it will be picking up the rows or the columns. And forest represents multiple trees, hundreds of trees or thousands of trees which you want to build. Now, random forest is a very complex algorithm. It involves multiple steps. Step 1, specify the number of trees to be built. Specify the number of trees to be built. The argument is n underscore estimators is equal to 1,000. We are asking it to build 1,000 decision trees. Like how we built in a single tree, such trees will be built, 1,000 decision trees will be built. Step 2, this is the core and the important step. The success and failure of the algorithm will depend on this step. Randomly create 1,000 samples of data from original data, wherein each sample will have 65% of randomly selected rows and square root of number of variables. Square root of number of variables randomly picked. So each sample will not have the complete data. It will be 65% of randomly selected rows. Let us say we have 10,000 observations. We have 10,000 observations. 65% of 10,000 is 6,500 rows. It will randomly pick 6,500 rows. Suppose we have 16 variables. Square root of 16 is 4. Each sample will have only 4. Each sample will have 6,500 random rows and randomly selected 4 variables. Not all variables will be there. Each sample will be like. Now, the method it uses is data with replacement. That means each sample is created from data universe again and again. Which means Observations which came in previous samples will also repeat in future samples. So data with replacement means observations and variables that appeared in previous samples will appear in future samples also. That means observations and variables will appear in multiple samples. Observations and variables will appear in multiple samples. Observations, and that is the objective of this algorithm. The objective of this algorithm is by making the observation and variables appear in multiple samples, thereby in multiple decision trees, the predictive accuracy will increase or the error will decrease. So the logic here is by making observation and variables appear in multiple samples, thereby in multiple decision trees, the predictive accuracy in case of classification and error in case of regression will be good. Accuracy will be higher, error will be lower, minimal. So that is the objective. And this model again was created to overcome the overfitting problem in decision tree. The reason why random forest algorithm was initially developed was to overcome the overfitting problem of decision tree. Random forest does not overfit like your decision tree, and it has good performance, better than decision tree. In this whole random forest, the sampling is the most important task. If anything goes wrong in the sampling method, the algorithm will stop. What I mean to say is, suppose you have 3 GB of data and you are creating 1000 samples of 3 GB data, it will be more than 3 GB, right? And you might not have enough memory power to process more than 3 GB of data. Then it will simply say memory error. Memory size error will come out saying that enough memory is not available. So this algorithm particularly needs lot of memory and computing power. So when you have large scale data, random forest works really well. The only disadvantage is computing power. It requires large scale computing power because the sampling process has to complete. If the sampling process is not completed, the algorithm will not move forward. So in this whole case, the sampling is the most important task. And the sampling it uses is data with replacement. So random forest sampling with replacement. It will use all the variables. The variables will come in one or the other sample. Here also same thing. You'll get variable importance. All tree-based models will generate variable importance. It will make some variable 0. No. In the output, based on the Gini and entropy, random forest also, see, random forest is exactly like decision tree. Only thing is, decision tree is a single tree model. Here you are building hundreds and thousands of trees. After building the trees, you aggregate the outputs for each observation, and then you come up with the final prediction. Other than that, everything is same. Same feature importance will come. Some variables will be found insignificant. Because yesterday we discussed it, right? If Gini is greater than 0.40, the variable will be automatically deleted from tree. If entropy and information gain is less than 0.50, it will be automatically deleted from tree. Same splitting methods, everything is exactly same in random forest, except you are building more than one decision tree. That is the difference. So you can see here, this is your bootstrap sample 1. You have sample 1, sample 15, 60. Sample means observations. Sample here means observations 1, 15, 64, 15, 22. So you can see there is observation, what you call second sample, where you have which observation repeating 58 or something, training sets, bootstrap 2, test set. So there will be repetitions. Here it is not showing, but there will be repetitions. Okay, and then each sample will have each one single decision tree will be built. And again, each sample will also have the test. It will also train the model and also test the model. So that is the process. So, and then it will aggregate the outputs. So this is the sampling method. Let us see if we can get a good sampling method. Okay, I think this would be better, color coding. Other than this. So this is our training data, which has different colors. You can see here, pink is coming 2 times, blue is coming 3 times, green is coming 1 time. In this sample, green is coming 3 times, blue is coming 2 times, light blue is coming 2, and dark is coming 2. In this time, 3 reds. So it is coming like sampling with replacement, bagging, bootstrap sampling. And then once the sampling is created, one decision tree will be created for one sample. One tree per sample. Bagging means data with replacement. So observations will keep on repeating in multiple samples. So observations and variables will repeat in multiple samples. Now, step 3. Once sampling is completed, parallel building of decision trees, one tree per one sample will start. Once sampling is completed, parallel building based on your system course, parallel, because each sample is independent, right? Parallel building is possible as each sample is independent. As each sample is independent, you can parallelly build trees. Step 4, after building the tree, prediction will also be done. Step 5, aggregation of predictions. Aggregation of predictions. In place of classification, majority voting, and in case of regression, average. Average method is used in case of regression. So one tree is built for each sample, and the prediction will also be done on the tree. And then if it is a classification problem, majority voting. Majority voting means observation 20 came in 100 trees. 75 predicted it as yes, 25 predicted it as no. So observation 20's final prediction will be yes. Similarly, observation 10 in regression came in 15 trees, and each tree predicted it as around 20 to 25 value. When you take all the values divided by 15, you'll get the average. So for regression, it is average. For classification, it is majority voting. The final prediction of each observation will be created. Majority voting means, like I told you, observations will appear in multiple samples. Observation 20 appeared in 100 samples. That means it will come in 100 decision trees. In 100 decision trees, it will be predicted. 75 decision trees predicted it as yes. 25 predicted it as no. So what is majority? 75. Final prediction of observation 20 will be yes. Same thing with regression. As many predictions as it generates, divided with that number of sum of the observations, divided by count of predictions, you will get the average. It will use average in regression. Majority voting in classification. So this is the random forest algorithm. So the core and the major step is the sampling. If you get any error in the sampling process, the algorithm will stop there. It will not go to the next step. So once you successfully complete the sampling, it will go to the next step of tree building and then do. Now, parallel building of trees. Parallelization is another thing which you need to understand in random forest. Since each sample is independent, we can parallelly build trees. Because each sample is created separately, right? So each sample has no relationship with other sample. So each sample is independent. That is why we can parallelly build trees. Based on a system course, 3-4 trees will be built at a single point of time, and all the trees will be being predicted like that. It will do faster. If you have good computing power, it will be very fast algorithm. Random forest. So this random forest algorithm was developed to overcome the overfitting problem in decision trees. To overcome the overfitting problem, it has been developed. It is both classification, not both, it is classification, regression, missing value imputation, and variable or feature selection algorithm. It's a very, very powerful algorithm used for multiple purposes. It is a classification algorithm. It is a regression algorithm. It has ability to do missing value imputations on its own. And it also is used in variable or feature selection method. So the only disadvantage is computing power. It will, you can do it as part of random forest preprocessing also. So as part of random forest algorithm, in the process itself, there is this missing value imputation. You can directly use, or when you are using when you are using it in mice algorithm, multivariate imputation chain, you can specify the algorithm you want to use. You can also have an option called RF. Random forest can also be used in mice. So you have an option of this. So here, let us see. N estimators by default is 100. N underscore estimators means number of trees. By default is 100. Criterion is Gini. Max depth none. Right? We said the max depth none. Then leave max features is square root of number of variables. Bootstrap is true. OOB score, random state, verbose, class weight, CC alpha, max self none. So in R, we have this option of use what we should do with NA. Here we don't have in Python, but in R we have the option of dealing with missing values. So a lot of things are there. You can balance here if you want. I think missing value in Python, it's not there, but in R we have. Okay. Then what is the case for them? We can just need to categorize the data. See, that pre-processing within the algorithm will take a lot of time. It is better to avoid, because if it gets stuck with pre-processing, you don't know what is happening, and it will take hours. That is my practical experience. There are algorithms where you can do pre-processing as part of algorithms, like neural networks, gradient boosting. There you can do, even in support vector also, you can do missing value imputation as part of the algorithm. But the problem is it will take a lot of time. Rather than that, you do pre-processing, let us reduce the time. Even in cloud environments also, they say first pre-processing has to be done by ourselves. Don't let the, because it eats away computing power and it eats away time. And cloud is charged per hour, right? So cloud timing is charged, cloud billing is done per hour, per processor per hour. So their computing power is also cost and time is also cost. So you have to make sure you're using less computing power and also the less time. That is what is happening. So most of the experimentations are happening in cloud. Okay, so or even if you're doing system based, you have to be, because most of the people give laptops 8 GB only, right? Companies give 8 GB RAM. Very few people get the 13 GB RAM laptops or anything like that. But most of the employees get 6 GB or 8 GB RAMs, right? So you have to look at the computing power also. And then let the algorithm, let us not have any interference with the algorithm.
Majority of thing is that we suppose 50% less than 50%
that scenario will not arise. That will not arise. In bootstrap sampling, that scenario will not arise. That is the reason why bootstrap sampling is used. Bootstrap sampling will never let that situation come up. Equality will never come, or equality of class predictions will never come in bootstrap sampling. Okay, so this is your random forest algorithm, which is a very powerful algorithm. It requires computing power, but very, very good performing algorithm. It has better performance than decision tree, slightly better performance than decision tree. It overcomes the overfitting problem of the decision tree. And the only problem it has is the memory error, or the computing power is the disadvantage. Now let us build this algorithm on Kaggle from sklearn dot ensemble import random forest regression. RF is equal to random forest regressor n underscore estimators is equal to 3000. Now there is no fixed formula for deciding how many trees we need. That is another question I get. It is based on your judgment. Generally, what happens is we can give a random value, and then if we plot the error, we will know at which point the error becomes straight line. In R, we get that situation where we can see the straightness of the plot. That way, we can finalize the number of trees. In Python, we have to write a loop and then we get it. Let us see if we can get that model also. RF model is equal to RF dot fit X comma Y. Number of trees. $98.27.
Again, give the result is like 0.9.
Huh. So let us see the cross validation. Cross validation should also be close. If it is closer to 95, 96, 90, above 90, then we can say it is not overfitting. Well, this is small data, right? We have only 1460 observations here. So random forest requires data greater than 20,000 observations. So you can see, right, all of them are close to 87. Decision tree, we have 60 to 89, right? In decision tree, the cross validation scores were very wide. In decision tree, the cross validation, lowest score is how much? 0.56, highest score is how much? 0.82. Lot of variation in the what you call R square. Look at this, all the R squares are closer to 85%, 81 to 88. So we cannot say it is overfitting because we are getting very close scores to one another. So this is not a overfitting problem. All of them are close. If you take the mean and p dot mean, and if you copy paste this array, you got an average of 85 or 86%, which is a good average, right? So random forest does not overfit like decision tree. In decision tree, if you take the average of all of them, it will be around 65 or 60%. That is a overfitting problem. This is not a overfitting problem. Here we have a performance which is better. Now, RF model, we are not calculating. PD dot data frame X dot columns, comma, RF model dot feature importances dot sort underscore index ascending is equal to false. And P dot round see, same thing we get overall quality and all. And we will get some variables with zero importance. See, some of them are zero important. Huh? Yeah, it will take time. It will take time run to run. It will take time.
Okay, this is not the brand. Yeah, if you are running algorithms from the beginning plans, they take and. Maybe क्या करा तेरे को उसको आया था ये आया होगा तो मतलब बना लिया तो ये कवर बोला ना it requires something depending on processor even processor even management what is the processor
Done? All of you got it? Still running it? Your, how much GB? 4 GB or 6 GB? 8 GB. Okay, 8 GB it should run. 4 it will take time. Might also generate a memory error. It's still running for you? No problem. Let it run. See, we have not calculated RMSE. The truth mean square error has to be calculated, right? So, pre-predict is equal to pre-model dot predict of X. NP dot SQRT, NP dot mean open bracket, y minus tree predict start 2. We got an R square of RMSE of 0 because the R square is closer to 99 point something, right? No, we got 1, R square of 1. Here we got RMSE of 0. RF predict is equal to RF model dot predict of X. So we will copy the same statement. The 10,430 we got for RF random forest predict. For regression, we got RMSE of 30,300. For regression, we got 30,300. For tree model, it is 0, but RF it is 10,438 RMC. But the problem with tree model is it is overfitting. Now, how do we check? By submitting the data into the competition site. That is the best method. Tree test predict is equal to tree model dot predict house test DM. PD dot data frame tree test predict dot 2 underscore CSV tree dot CSV. RF test predict is equal to RF model dot predict house test DM. PD dot data frame RF test predict dot 2 underscore CSV RF dot CSV. Now, if you submit these predictions on the web competition side, Kaggle side, you will come to know what is the accuracy, what is the R square, and we will know the rank. Huh. So after that, see, we are predicting on test data. We are given this the test file also, right? We are given the test file on which we are predicting. Now, that test file prediction, I am writing it into a data frame and to a CSV file. So if you go to my hackathon folder and house prediction, date modified today, see, there is a file which is written as tree.csv. So these are the predicted values. These are the predicted values. And if you take sample submission, this is the sample submission file. I will copy the predicted values, Control Shift down arrow, Control C. I will go to the sample submission file. I will not touch the header cell. I will come to the B2, Control V, Control S. Okay. Now I will go to the website, Kaggle house price prediction. So last class we submitted regression, right? 7 days ago. We got 0.35612. So linear regression when we submitted, we got that. Now let me submit Test prediction, sample submission. Precision free, make submission. See, 0.2031. Drastically it improved, almost 0.15, 2806. Not 2806, okay. It has drastically improved. Now, let me submit the random forest score also. The other one which we have calculated is random forest. These are the random forest predictions. Control Shift down arrow, Control C, sample submission file, Control V, Control S. Now I will go to the same side. So remember how much we got? 0.2031. Submit prediction. Sample submission CV. Random forest, 3000, right? See, 0.14. How much drastically it improved? See, 0.14. 0.14 is a very big improvement, right? So you can see, jump to your position on leadership board, 1916. Where is 0.35 of a multiple linear regression, 0.20 of decision tree, and 0.14 with random forest. Sequence of algorithms, base to advanced algorithms. This sequence you always remember. So we don't jump to the random forest. We know random forest will perform better. Sometimes we always have to stick with the basic algorithm like linear regression also. Okay. See, in competitions, this matter. Highest accuracies, scores, and all matter. But in real-time problems, getting a result with acceptable range is a enough process. Okay, we don't want to complicate things. Right. So MLR will be best option then. Right. Here, see how much drastically it improved. See, improvement in submissions. You also can submit the scores. Okay. These are the predictions. You calculate RMSEs and then you submit the predictions also in your, you all registered, right, to this competition. Submit the scores. This will help you as your GitHub project, where you can upload this into your GitHub profile and then discuss, write something like how the accuracy, how the R square improved or RMSE. The metric is RMSE, how the RMSE reduced as we use advanced models. Okay. It's still running. You want to see the feature importance? This is the feature importance. Done? You have done. Now you can go then with this. Pre-predict and then RMSE and then the final 2.6.
I think it's fun. They data costing, regulation model, model specification, differentiate, and something model explanation. Yeah, and like just extra every day, but the district मेरा तो आइटम
Running? That's okay. Go there, delete the ID column. How says the ID, you might have missed the ID column, deletion of ID column has to be. Dot drop, I capital, B small letter. See, we have dropped that here. Here, house test DA, drop ID. Or print column, since if ID is there. It's there, then you have to drop it. That is the only differential column. Grant for you? No. You should never stop random for this. Let it, okay, then you write it at home. Don't try to wait anything and you'll hang your process. Because it allocates memory in process. So that multiple memory allocation will slow down in the process of control. Only thing is practice. Until then, we open the previous one. Always keep the notebook. By the time we next week or the other week, we have about a couple of notebooks in integration classification with all models. So that will be a reference point. Whenever you want to do a working on any data, keep this notebook active along with your working data. After some time, you'll automatically do it. It's only practice. It's only practice. Without one to practice that by next to by end of this by October end, we complete all months, including your numbers. Okay, then you have two notebooks, one in regression, one in classification with all the models. Great. Now, whenever you have any doubt, you can open them and check the commands and copy them there, and then you can copy. And over a period of time, once you work on multiple data, you will get your other comments. That's what I think is doing. Once after building all the models, once you work on 5 data sets or 6 data sets, we have done only 3 data sets are working. We will go into other data sets also. And there is a hackathon also going on. I mean, till 2nd October. So I will it will ask for an MCQ test. Once you do the MCQ test, you score 15 out of 30, you will get access to the data set. So I think other that students might already have started downloading. So I'll ask them to send the data. So that data will help us to look at the real time scenarios. So at least 2 different ebook notebooks to keep in always in screen. Fully clean the notebooks without any errors. That will be a reference notebooks. Whenever you have any doubt, you can go to those. And by end of November, we will have a complete notebook with imbalanced data balanced in classification. And in regression, we also have that what we call regularizations done and all those things done and all. So then your reference notebook will be your all models and the comparisons and all. You can upload them into your GitHubs with the write down little bit note of your interpretation and analysis. and you can upload them to GitHub permanently. And GitHub anyway, you can access from your office from anywhere, so that will be a reference point. Okay, you'll take a break. Once you're done, you can take a break. The data is like only numerical requirement, so rules will be created. If then rules will be created. So copy this rules here. So get rules 3 x dot columns y. Okay. So we got the rules here. Now see, you can see here. Very lengthy rule. If overall quality is less than 6.5 and overall quality is 5, if the overall quality is between 6.5 and 5.5, living area is greater than 1378, garage cars is 2, kitchen average above grade is 1.5, living area is 2, 1, and then various other conditions subtrees. The final predicted value is 2,08,500. Similarly, the second rule, you can see here, this is the second rule. And then this is the predicted, again 2,08,500 is the predicted value for the second rule also. The third rule starts from here. Yeah, it is also predicting 2,08,500. 2,08,500 is common prediction, and any other change in values you can see here. This is also 2,08,500. 500. 500 rules. These are all about 2,08,500 rules. There is the other 2,08,000. And everything is coming for 2,08,500. I think class it is predicting it wrong. Actually, this code is created for classifier. This is not good for regression. This is for class name, see? So that's the problem. But actually, if you see the areas, there are different rules created for different predicted values. So that is because the problem is this is for classifier. That is why we are not getting it correctly. I'll try to find the rule for regression model. Otherwise, it creates rules, and these rules are used for prediction. It's a rule-based prediction system in tree-based models. So you'll be getting us based on that. Whatever it will look at the whole observation and compares it with the rules. Whichever rule fits 80%, it will give that value. Actually, in R, I'll show you the rules. The rules will come in R. So this is not a statistical software, no? So we don't get the rules here. Yeah, house price prediction. So, library alpha dot plot alpha dot rules alpha. So here, these are the rules it will create. So sale price is 1,18,199. When overall quality is less than 8 and neighborhood is boost and BR Dale dark side or right bitter or all this is one complete rule. Okay, sorry, till here. Till here. And then predicted value is 13539 based on this rule. Predicted value 15. Then 207,186, 249, 258064, 3148, 3534. So it will create rules from the tree, and then these rules are used for prediction. So it's a rule-based prediction system, which is used by decision tree model. So you'll have repeated values. Values will repeat. The limited values will repeat in your prediction. Okay. No. Random forest, what happens is rule-based prediction will be done and then majority aggregation will be done. All right, we'll move forward. Now, multi-tree models. Tree-based models. Multi-tree models. Ensemble methods. The second type of method is boosting. Boosting is the second type of the method, and the very popular algorithm is gradient boosting machine, also called as GBM. Bagging is one type of ensemble method. The second type of ensemble method is boosting. Popular algorithm is GBM, also called as gradient boosting machine. GBM is both regression and classification model, which is developed exclusively to improve the accuracy or reduce the error by targeting weak learners or wrong predictions. So boosting machines, GBMs, are exclusively developed to work on wrong predictions. They were exclusively developed to target the weak learners or wrong predictions. Now the process is this. Step 1, specify the number of trees to be built. Say n underscore estimators is equal to 1000. Okay, step 1 is you have to specify the number of trees to be built. Step 2, create sample 1 with 65% randomly selected rows or observations and square root of number of variables, right? You will create sample 1. Step 3, build decision tree for sample 1 and also predict. Step 4, identify the wrong predictions and move them to sample 2. So step 1, you specify the number of trees to be built. Then step 2, create the sample by taking 65% of randomly selected observations and square root of number of variables. And then immediately it will build a decision for sample 1. And prediction will also be done. Then it identifies the wrong predictions and moves them to sample 2. Step 5, replenish sample 2 with data and add weights to wrong classifications from sample 1, from tree 1. So you will replenish the sample 2 with other data from the data universe, and you will also add weights to the wrong classifications. We will give weightage to the wrong classification. 0.10, 0.15, some weightage is given to the wrong classifications. No, leave it open, leave it open. Wrong classifications from tree one will be given more weightage. 10%, 20%, some weightage will be given to those wrong classification. Now, what it will do? Step 6, it will build decision tree 2 for sample 2 and predict. Step 7, identify wrong predictions and move them to sample 3. And this process will go on till the iterations are completed. 1000 trees are built. Misclassification, na? Actual versus predicted in classification. In case of regression, if the predicted value has too much of variance, suppose the actual predicted value is 1 lakh, actual value is 1,45,000, the price of the house. The predicted value is double that, 2,90,000. That means it's misclassified, wrong prediction, right? So it will be moved there. If it is 1,55,000, it will not look at it. If it is more than 50% above the actual value, then it will take it as wrong prediction in regression. In classification, straight away, classes. If it is original class is 0, predicted 1 means wrong. Original class 1, predicted 0 is wrong. So it will move them to the next. So that's how it will identify the misclassifications and wrong predictions. Once this, so here, what is the thing is, each tree is dependent on previous tree per sample. Each tree is dependent on previous trees per sample. Here it is sequential building of trees. Sequential building of trees. Whereas in random forest, it is parallel. Each sample is independent. You build a parallel tree for one tree, one sample. Here it is not possible. Until tree 1 is not completed, you cannot have sample for tree 2. Until tree 2 is completed, you cannot have sample for tree 3. So this is a sequential building of tree. And each tree is dependent on previous trees per sample. And misclassification and wrong predictions will be given weightages in the sample, so that they can be targeted and pushed towards right predictions or right classification. So that is what happens in boosting. Because if you give weightage to that wrong prediction, it might, what we call, push towards the right prediction. Like lambda in regularization, here, if you give more preference to that, see, generally what happens is, in most of the models, larger values have a bias. By making it a larger value, you are creating a bias towards the thing. So that is what boosting is all about. So see here. See here. Here you have this is the first decision tree. Plus and minus, 2 classes are there, right? Now these three are wrongly classified. These three are wrongly classified. So what happens? More weightage is given. See, the size is increasing and a new boundary will be drawn. Now again, these three becoming wrong predictions. Now these three will be given more weightage. And then finally, you can see here, this is the box 4 where all of them are categorized into 2 distinct classes. So weightages have to be given. So the boosting is the boosting targets them. See, it tries to fit the new predictor to the residual errors made by the previous predictor. It tries to fit the new predictor to the residual error. It will take the error as the weight. Okay, and then it adds it to the value, hoping that the prediction value will be correct. So fit the new predictor to the residual errors made by the previous predictor. So this is what gradient boosting will do. It will use the previous error and then try to improve it further. That error will be added as the weight. Now, this diagram will give you the difference. In a single decision tree, you will get a single tree. In bagging, you have sampling, one sample, one tree. One sample, one tree, bagging, random forest. Look at boosting, one sample, one tree. One tree to sample, sample to tree, tree to sample, sample to sequential. This is parallel. This is one single decision tree. So this is the difference between, in interviews they'll ask you, what is the difference between a decision tree, random forest and boosting machine? The difference is the way they are sampled and they are built. So in boosting, wrong predictions will come frequently, right predictions will come less frequent. Wrong predictions will be coming more frequently in the data, right predictions will come less frequently. Whereas the occurrence of observations is equal in random forest. Each observation has its own equal weightage to appear in multiple samples. Here, weak learners have an additional weightage compared to the correct predictions. Okay, so bagging random forest is parallel. One sample, one tree. One sample, one tree. One sample, one tree. Whereas boosting, one sample, tree. Then again, second sample. See, the arrow comes from the second sample is created from the previous tree. And then tree will be built. Again, third sample will be created. Then it will be. It's a sequential building of trees. This is the difference between tree-based model, single tree model, multi-tree models bagging, and boosting. Boosting has better performance because it targets better level, slightly better performance than random forest. It will have a slightly better performance compared to random forest. So boosting methodology is what you can see here. This is very important, boosting. And in most of the competitions, we see boosting becoming what you call boosting. There are variants of boosting like XG boost, what you call the extreme gradient boosting. XG boost is a very popular algorithm which wins competitions and all. Extreme gradient boosting, XG boost, we call it as XG boost. So this is your bootstrapping. See, this is a bootstrap sampling, which is your bagging sampling. Then if you scroll down, the boosting sampling. Okay. We have the weighted, this is the original data. Hello. See, these are wrong predictions, which are given more weightage. Greens and blue are very less, right? Hardly any greens are there. And then wrong predictions will go to the weighted data and then classify. This is the boosting sampling method. So boosting is also very powerful algorithm, but it requires less computing compared to random forest. It requires less computing required than a random forest. Yeah, it is recording. So this is the understanding of gradient boosting. See, tree splitting methods are same. Tree splitting methods are same. So tree splitting methods for both random forest and gradient boosting are same like decision tree. So we have talked about in the yesterday's session, right? Decision tree, the two what we call the formulas. See, Three splitting methods are same: Gini, entropy, and information gain. So same methods are used here also: Gini, entropy, and information gain. Lowest Gini first spread. That's what we did in yesterday's what we call Excel sheet. Also, we calculated them, right? So we got that same Gini and entropy. Same methods are used in random forest and boosting machines. Probability based calculations. Okay. Yeah.
Sample one,
Hmm.
under the wrong prediction is going to the sample. Only those wrong predictions will go to the sample. I will take from open data from the.
Or to replenish. You have to replenish the data. The original data also, some observations will come back. It will not take the wrong predictions. Other data points it will take and replenish the data. If you look at the sample size here, it is the same, right? It has to replenish. That's what I said. No, replenish. Replenish means take the data, remaining data from the original data. See, replenish sample two. That means it has to become 65%. That means it has to go to data universe and get more randomly selected observations into it. But it will make sure that the wrong predictions does not repeat again. It has to replenish the data. Every time it has to replenish the data. And then sometimes 10% data might have to be replenished. Sometimes 50% data might have to be replenished because it depends on the wrong predictions. Okay. Now let us build the gradient boosting. From sklearn.ensemble import gradient boosting regressor. GBM is equal to gradient boosting regressor n underscore estimator with 3000. GBM model is equal to GBM dot fit x comma y. Ran fast. GBM model dot score x comma y. See 99.96. Comparatively better score than random forest. So to check whether it is overfitting or not, GBM comma x comma y. Cross validation is repeated testing with the subsets of the data randomly chosen. See, all of them are close to 90. Entry dot mean will check. .66. For random forest, we got 85.94. Here we got 88.66. But slightly better than random forest. Okay. Now let me predict on the test data also, so that you can see. GBM test predict is equal to GBM model dot predict house test here. PD dot data frame GBM test predict dot two underscore CSV GBM dot CSV. So let me just check once with the status. Model hackathon. First price prediction, GBM, open with Excel. Sample submission, open with Excel. So, Control Shift down arrow, Control C. Control V, Control S. Then table, submit prediction. Desktop. Hackathon, first price prediction, sample submission. GBM 3000. Next submission. See 0.13. 0.5 less than random forest. It went jumped by 70 points, 70 positions points. So 1411. 0.13698. Better performance than random forest. Not that exaggerated, but slightly better performance than random forest. So this is how the model performance improves as we go from base models to advanced models. So always start with the base models and then go model by model and then understand. So when you go model by model, you will also understand the variables. Right. And then you'll be able to build advanced models easily. See, in advanced models, there will be two problems. Variables will be problem, hyperparameter tuning. Hyperparameter tuning is a problem. Now, if you look at the random forest only, how many arguments can be given? We might talk about hyperparameter tuning at a later stage. sklearn random forest. See how many arguments you can give. These are called hyperparameters. For a regression model, we don't need to give this many arguments. But look at these models. From tree-based models onwards, the amount of parameters or hyperparameters we need to specify will drastically increase. Now, sometimes for large-scale models, we have to play with them. Suppose if you are not able to build a proper tree, then we have to play with max depth. You have max depth here also, right? Number of levels or layers in the tree. That has to be adjusted. So the hyperparameter tuning is very important when you go into advanced models. Similarly, if you go to neural networks, you have to decide a lot of parameters. If you don't do these parameters correctly, your models will automatically fail. See, and similarly for gradient boosting also. So we're using regressor, right? Gradient boosting regressor. See, so much of things. Loss, learning rate, estimator, subsample, criterion, mean sample sleeve, max depth is by default 3. Mean purity, random state, max features, alpha. So there are many of these parameters which you need to be given. So we go in Python, what happened is the researchers have set the basic parameters based on the what you call their experience and the community, they have fixed the basic parameters. So in Python, we don't need to worry about the basic parameters, but when you're dealing with R, the basic parameters have to be fine-tuned by us only. R, we have to give the fine-tunes. So there we will be using a lot of grid search, a lot of multiple parameters, multiple arguments, we have to give them. But in case of Python, most of the hyperparameters are fine-tuned already by the community as per the model performance, right? So if you look at random forest, they didn't specify max depth. Here they have specified max depth as 3. Because it's a sequential building. If you don't specify depth, then every tree will be a larger tree, then it becomes a problem. So that is another advantage in Python. The hyperparameters are fitted in such a manner. The community has already fitted hyperparameters for most of the models. So we go with default models. Very rarely we change those default models. Only if it is not fitting, then we go and look at the default parameters. But in case of R or SAS or any other software, we have to fit our own parameters. Default parameters will not be fit. Now, our community is also doing the same thing. They are also decided to set the base hyperparameters for models like in Python, so that it is easy for us to build the models. So in fine tuning, what happens is a 0.001 change also creates big problem on large scale data. On large data, a learning rate of 0.001 also is a big difference. So you have to be very, very careful when you're tuning large scale models. So generally what happens is systems will do large scale tuning. They give computing power. Amazon and Netflix and all, they use systems to do parameter tuning rather than the humans. I think they give a range of values, and the machines will keep on running the range of values, and the best fit parameters will be identified by the machine itself. Now, on the HR analytics data, which is the classification data, fit these two models. Yesterday we worked on HR analytics data, right? Open that HR analytics data, run all the cells, and fit this both random forest and GBM. They are classifiers, not regressors. HR analytics is classification, right? So use classifier. So from sklearn.ensemble import random forest classifier. Random forest classifier and underscore estimators. This is a large data, right? So we'll give 1,000. RF model is equal to RF dot weight X comma Y. Because we have 50,000 observations, right? Yeah, trying comparatively faster. Score X comma Y. 99.97. Okay. Cross val underscore score RF comma X comma Y. So in decision tree, we had a good score yesterday, right? There was not that much of overfitting. Let us check for random forest. What is the amount of overfitting? See 93. No overfitting. Right? Repeated testing 93. Compared to decision tree, this is far better, right? Now, this is also competition thing, actually. Tree test predict is equal to tree model dot predict HR test DF, right? Oh, what happened? Excess 13 features, expecting 12 features. So I think I have to remove ID column, employee ID. SPF dot columns. Yeah, employee ID is there. It's the problem. HR test DF is equal to HR test DF dot drop single quotes employee ID comma access is equal to 1. Now we got the predictions, right? PD dot data frame retest predict dot two underscore CSV dot CSV. Now, this is analytics with their competition, hackathons, HR analytics, right? There is HR analytics. Okay. Now, we have to go to hackathon. There is HR analytics. Yeah. So tree.csv open with Excel. Sample submission open with Excel. Okay. So we copy from this 0, control shift down arrow, control C, paste them here, control V, control S. Now let us submit on the analytics Vidya site. Solution checker, update solution file, desktop, hackathon, HR analytics, sample submission, click open. This is what? Precision tree. No, add solution. See, 0.41. Submission is 0.41. Okay, which is little, which is okay. 0.41, but if you look at the leaderboard says 0.54. We have 0.41 for decision tree. For decision tree, I got 0.541. Now, RF test predict is equal to RF model dot predict HR test DF. I am predicting on the RF. So PD dot data frame RF test predict dot two underscore CSV RF dot CSV. Now I'll go to the same place where you can see here RF open with Excel and then copy the sample submission from 0, control C, sample submission, control V, control S. Okay, now let me submit the random forest. Whether it improves or not, let us check. So solution checker, upload solution file, sample submission, RF, we have used so many 1,000, right? No, add solution. 4164, marginal improvement compared to the 4132. So you can see here submissions 4164 compared to the decision tree. I think if we can improve to 3,000 trees, this will go a little bit to 4.2. What was my random forest earlier? 4.2. 4.259 if you give 3,000 trees. If you give 3,000 trees, it will go up to 4,259. Okay, because we have given only 1,000, na? So it is like that. But if you give 3,000 trees, I think this will definitely go to 4,259. This is how the performance you can check. And then understand the model, and then we will be using the model. So all of you random forest ran. You can look at the. Cross underscore val score you have to define from top. S3 you might from sklearn dot model underscore selection. From sklearn dot model underscore selection. Yeah, it will become. Anyway, come down. You can hire some. From sklearn dot model underscore selection. Cross underscore info cross underscore file underscore. Model selection. Got it? Cross. See, that is slowly remove the temp file. Because Python constantly creates temp files. You can know the question. And local every time checkpoint creates it stays. So you have to remove this temp files constantly. Okay, RF is done. Gradient boosting classifier, GB classifier. From sklearn dot ensemble import gradient boosting classifier. GBM is equal to gradient boosting classifier and underscore estimators 2000. GBM model is equal to GBM dot fit x comma y. When it is running, let us see what Jobathon thing they have given. Email address, all of this. Gmail. See, they're asking your GitHub link, LinkedIn link, and Kaggle link. So you have to maintain GitHub projects and also connect them to your LinkedIn. LinkedIn also has projects, right? And then your Kaggle also. We will work on a couple of projects in Kaggle also. So SQL, machine learning, dashboard. Not looking for jobs. Expected CTC. Okay. So problem statement is given. Oh. So problem statement is which Go Shop is an online e-commerce company. Objective is your task is to implement an ETL process and generate a table which will help the information to know more about its user base. Okay, submission file. You have to create an ETL table or they change the format. There is more towards data engineering, not data science or data analyst. This time it's purely data engineering. PySpark assessment. So this is data engineering position, not a data analyst or anything. So the skill test have 40 questions with each question. Python, SQL, PySpark, Hadoop, and Hive. So this is purely data engineering job or data cloud engineering. Let us see if I can do ETL. I'm trying to do, but I'm not finding the software to do it. IBM model dot score X comma Y 94.70. If we make it 3000 in the score increase. So next session, we will start with new data. So we will start with, there is a website called Driven Data. There is a flu vaccination prediction, seasonal flu prediction and H1N1 prediction. Two dependent variables will be there. So you can build two sets of models, classification data. Seasonal flu is a balanced data, H1N1 is a imbalanced data.
The beginning and interest rates had 13 people, but recently classification is expecting to.
Employee ID.
Yes, sir. Talking that
Print columns, did you drop it correctly? HR test DF, not HR test. Dot columns. Got it?
Sir, I was telling.
Yeah, that's all. See, that's what now autofill. Tab, always use tab. 95% mistakes are spelling mistakes only. $94.87 for 3000 trees. GBM test credit is equal to GBM model or credit, which are test df. GBM dot data frame, GBM test credit dot to underscore CSV, GBM dot CSV. Sorry. Sorry. Okay, got it. 49.73. See, GBM drastically jumped up. It is 49.73 for 2000 trees. For 3000 trees, it will give you a little bit more accuracy level. See, 49.73 GBM, 2000 trees. Excel sheet I forgot yesterday, I'm sending it today. Sent it all files.
No. No, yeah. ఎప్పుడు సార్ సరే వాళ్ళని
Okay, run dots.